Hi everyone, this is Sarah Shuri from University of Michigan, and I am going to talk about our work Siamese learning-based monarch butterfly localization. Each fall, millions of monarch butterflies across the northern US and Canada migrate up to 4,000 kilometers to overwinter in central Mexico. However, the number of monarchs completing this journey has dramatically declined over the past few decades, and tremendous resources have been invested into monarch conservation. We are also contributing to this effort by developing a tracking technology for monarch migration. This technology can be indeed a key to have a detailed understanding of the habitat used during the migration. So for tracking the monarch butterflies, one possible option is using GPS-based geolocation method, which is the most popular and accurate method for tracking larger animals. However, the lightest tag, which is 1 gram, which is too heavy for monarch butterflies. Also, it requires a power-hungry system, which is not feasible for a 3 month operation with a very small battery. Another possible option is using light and temperature-based geolocation method, which is less accurate than the GPS method. However, with the Michigan Small Animal Integrated Logger called MCEL, we can achieve a 62 milligram tag, which can capture multimodal measurements like light intensities and temperature with ultra-low power consumption. Here we can see the pictures showing the MCEL system while attaching into a monarch butterfly. The first figure shows the proposed embedded system for MCEL, and the second figure shows the attached sensor in both closed and open wing configuration. So for tracking the general scheme, we first attach the MCEL sensor to the monarch butterflies across the northern US and Canada before the migration starts, as shown in this picture. Then, while the monarch butterflies travel southward, the loggers keep recording the light intensity and temperature measurement with a corresponding time step over a 3 month period. As you can see here in this picture, the blue curve shows the light intensity and the red plot demonstrates the temperature measurement. When the monarch butterflies arrive in central Mexico, we go to their overwintering site and read the recorded light and temperature data wirelessly. Finally, we analyze the recorded light and temperature measurement offline using deep learning-based method to estimate the daily location of the monarch butterflies. Based on these estimations, the entire migration trajectory can be reconstructed, which is the main purpose of our paper. So given a light intensity and a temperature measurement on the DT, the goal is to estimate the position, meaning latitude and longitude coordinates that these measurements belong to. So the solution that we use to solve this problem is performing a coarse-to-fine grid search. We first generate a 2D coarse grid that covers our entire study area. Each cell in this grid has a specific latitude and longitude coordinate. Then, for each cell in the generated grid, we compute the probability that a given light and temperature belongs to that cell. And we repeat this probability estimation for all existing cells in grid G. Now that we have the probability for a coarse grid, we refine the spatial resolution of the likelihood estimation using 2D linear interpolation to produce a finer grid search. Finally, from the generated probabilities in the grid, we assign the estimated position to the cell which has the maximum probability and highest likelihood. As a result, we want to model a likelihood as output of a neural network. For simplicity, we assume that the light intensity and temperature are independent, so the likelihood can be separated. So for our case, we model the light likelihood and temperature likelihood separately using two different neural networks, psi-L and psi-T, as shown in this figure. First, we start with the light likelihood estimation, and the question is how we can compute the probability that a given light belongs to a specific grid cell. We know that the slope of the sunrise and sunset transient is highly correlated to the recorded locations. For example, we know that sun sets more slowly at high latitude than the equator. We built our algorithm upon this fact, and our idea is that two closely located data on approximately the same day, for example, even in different years, should have highly correlated patterns. Hence, we have our method Siamese learning-based localization. Here is an example of the pattern correlation for the light intensities which are captured at different latitude coordinates and same longitude coordinates. These lights are measured around equinox, and as a result, they have almost the same day lengths. However, we can see that the slope of the closed locations shown in the red and green have similar patterns, and they look different than other lights shown in blue and pink lights. So the question is how we can apply this idea of pattern matching to compute the light likelihood. We first generate a reference library which contains all the reference recorded light intensities and their known locations around date dt. Then to estimate the probability for given cell X, we find the subset from that reference library in which their locations are closely located around cell X. Specifically, we search for the locations that their absolute difference with respect to cell X are less than 1 degree. To make the computation of the pattern matching score easier, we apply few pre-processing techniques. We first apply the denoising adversarial autoencoder to denoise the light intensity. Then we calculate the night center for the reference light intensity. And finally, we align the light measurement LT based on that reference light intensity. And in this case, if the light measurement LT and the reference light have closed locations, then the aligned light will be completely in center of the reference light as shown in this figure. But if they are captured in different locations, then the aligned light will be shifted with respect to that reference light. So after that, we compute the pattern matching score between each light in the subset reference library and each light measurement. This score defines how similar and how correlated they are in terms of pattern matching and shapes. So we model the pattern matching score as output of a mapping function. And to construct the mapping function, we use a Siamese neural network model, which are twin neural networks that share the identical weights. So each network takes one of the light intensities and generates the corresponding latent vectors. Then to compute the matching score, we calculate the Euclidean distance between these latent vectors. And the idea is that if the light intensities are similar, then the latent vectors should be similar as well. To train the Siamese neural network, we need to generate the positive and negative sample. Positive samples are defined as data whose distance difference are less than 55 kilometers, and negative samples are defined as data with larger distance. We utilize the contrastive lights to train the model, which aims to maximize the similarity score for the positive sample while minimizing it for the negative sample. Now that we have the similarity score between a given light and each element in the reference library, we convert the calculated score to the probability estimation using a special softmax. This probability quantifies the possibility that the light LT belongs to that specific reference location. Then we compute the defined probability for all the elements in the subset reference library. Finally, we estimate the probability that a light LT belongs to a specific cell X as a mean of probabilities for all elements in the subset reference library. This probability is a likelihood that we mentioned earlier. We apply a similar approach to the temperature measurements to compute the pattern matching score. In this case, the reference library is taken from the weather station data, and at each grid cell, we compute the similarity score between a given temperature measurement and a related weather station data to compute the temperature likelihood. Here we show the comparison between weather station and sensor data at different locations. For the first figure, both temperatures are captured at closed locations and can be seen that their patterns are highly correlated. But as for the second figures, both temperatures are captured at different locations, so they look different in terms of patterns and shape. For data collation, we distribute Hubble sensors to volunteers all over the US, and we collect the real-world measurements for the light and temperature measurements from 2018 to 2020. In total, we collected around 5,658 days of valid measurements, and you can see the location of volunteers in the map shown here. So for the structure of the light intensities, we use 4 convolutional layers and 2 fully connected layers. And for the temperature measurements, we use 2 convolutional layers and 2 fully connected layers. Here we show the example of likelihood heat maps for two different dates, each row for 1 day. The grid resolution is 0.1 and the grid size is shown in here. The first column shows a light likelihood estimation, and we can see that both of them performs well for determining the longitude range, but their performance in the latitude covers larger area. Also, this problem can become worse when the dates are close to equinox because of the day length similarity. So to compensate for the latitude estimation error for the light data around equinox especially, the temperature measurements become really critical. In this figure, the second column shows the temperature likelihood estimation, and we can see that different from light likelihood, the performance becomes better on latitude than longitude. The third column shows a combined likelihood for light and temperature, and we can see that temperature helps to regularize the heat map, and the final heat map provides a more focused one around the ground truth. We also evaluate our method using an experiment by an MCell. The sensor was attached to a wild monarch butterflies on September 17, 2021, and the monarch was released into a wild day for a day, and then its sensor data was captured wirelessly while the butterflies was resting on a tree. We can see that our method successfully estimate the position with respect to the ground truth. Here to evaluate the quality of our work, we compute the absolute localization error and compare our method with the baseline. The first figure shows that the performance comparison between our proposed method and the state of the art using MSE, which is evaluated bi-weekly. All the results in this figure are based on the volunteer data. The second figure shows the CDF of error in longitude and latitude degree. We can see that our algorithm outperforms the baseline, especially around equinox, and it can prove that the pattern matching techniques can significantly compensate for low length variation issue around equinox. In summary, we develop a Siamese learning-based model using light intensity and temperature measurement, and the proposed method significantly outperforms the prior method, especially around equinox. And also, we were able to demonstrate successful localization of a wild butterfly using real-world data. Finally, our model exhibits a mean absolute error of 1.41 degree in latitude and 0.39 degree in longitude for the volunteer collected dataset. Thank you for listening.